Greetings. Greetings, guys. This is a recording for 13.3 geometric sequences. So let's look over that. Last time we looked at arithmetic, where it's adding or subtracting to get new terms. In a geometric sequence, the same number is multiplied over and over again to get to the new, to get to a new term. So let's look at some. 2, 6, 18. These are multiplying by 3. So 18 times 3, I don't want to do that in my head right now. Sorry. 18 times 3 is 54. Times 3 is 162. Times 3 is 486. I'm pretty sure. Times 3, times 3. Yep. So the pattern here is they're multiplying by 1/3 to get each new term, right? What about this one? 32, negative 16, 8, 4, except careful, positive, negative, positive, negative. This next one's going to be positive 2, then negative 1, right? These, you say, it's dividing by a negative 2, but I want to put it in terms of a multiplication. Dividing by a negative 2 is the same as timesing by a negative 1/2. So sometimes these sequences, if they alternate positive, negative, it's going to be a negative that is being multiplied by. And if it's getting smaller, think of it's multiplying by some number that's smaller than 1, okay? So let's look at this. A times r to the second, a times r to the third, a times r to the fourth, a times r to the fifth, a times r to the, what? Well, let's think about this. This is the first time, and there's no r's. Second term, 1 r. Third term, 2 r's. Fourth term, 3 r's. Fourth term, fifth term, 4 r's. Sixth term, 5 r's. The nth term, n minus 1 r's. See it? A is the first term. R is the common ratio, or it's what you have to multiply to get to the next term. The nth term, and this is a formula to memorize, one you've seen before actually, is the first term times the ratio to the power of n minus 1. Okay, there's your generic formula for a geometric sequence, and we're going to use it. Check this out. A few examples. This term is geometric, but wait a second. My geometric sequence looks like this. A sub n equals the first term times the ratio to the n minus 1. I don't see an n minus 1 here, and I don't see a term times a term. So, what's going on? Well, the first term is just going to be 3 to the power of 1, which is 3. Okay. What's the ratio going to be? Well, the second term is going to be 3 to the power of 2, which is 9. The easiest way, so this is going to go 3, 9, and the next will be 27, 81, and so forth, because it's multiplying by 3. Oh, it's multiplying by 3. Oh, so the ratio is equal to 3. Well, why doesn't it look like this? Check this out. If I put it in this form, a sub n equals 3 times, that's the first term, 3 to the power of n minus 1. Well, why isn't that there? Well, this is 3 to the first. And a long time ago in a world far, far away, we learned if I'm multiplying two exponentials with the same base, I can add their bases. So I add the exponents, 1 plus n minus 1. Well, 1 plus n minus 1, the ones cancel, and I get 3 to the n. The key thing you're always looking for when you're trying to see a geometric sequence is the variable is in the exponent. This is a lot like an exponential function. In fact, exponential functions are equivalent to geometric sequences other than the domains. Okay? A guaranteed way to find the first term is to put in a 1 into the equation. Guaranteed way to find the ratio is find two terms back to back and divide them. 9 divided by 3 is 3. 27 divided by 9 is 3. 81 divided by 27 is 3. Okay? So, keep in mind, just like arithmetic sequences, these could be simplified. Sometimes they won't be, sometimes it will be. So check this out. Find the first 5 terms and the 15th term. If the first term is 3, so 3, and the ratio is 2, so I can go 3. Oh, times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. Cool. Now, I could continue to find the 15th term, but let's look at the formula. The 15th term is going to be equal to the first term. I'm just using this, which is 3, times the ratio to the power of 15 minus 1. Well, 3 times 2 to the power of 15 minus 1 gives me a big number, 49,152. It's a big number. Cool. Find the 22nd term of this sequence. 9, 3, 1. The next term is going to be 1/3, right? And then 1/9, 1/27. I don't want to keep going because that's going to be too small. So the 22nd term, well, that's going to be, I just use the formula up there. The first term, which is 9, times the ratio, which is 1/3. If I'm not sure of that, take a term like 3 and divide it by the term that came before it. 3 divided by 9 gives you 1/3. So 1/3 to the power of 22 minus 1. Somehow that's going to be a very small number, I think. So 9 times 1/3, I'm just typing this in my calculator, to the power of 22, to the power of 22 minus 1, that's just 21, gives me a number in scientific notation. It gives me 8.604, I'll round it there, times 10 to the negative 10. Well, that's 0.000000000 8604. Wow. Check this out. I could also write it like this. 9 is the same as 3 to the power of 2. 1/3 is the same as 3 to the power of negative 1. 22 minus 21 is 21. So I've written this all as powers of 3. I could do this. 3 to the power of 2 times 3 to the power of negative 21, because 1 times 21, right? And 3 to the 2, 3 to the negative 1, 21. That's 3 to the negative 19. So this is 1 over 3 to the power of 19. And 3 to the power of 19 is probably a number that's too big for my calculator to figure out. Oh, no, it's not. This is cool. 1 over 116,226,1467. I think this would be fine, provided you showed you used the formula. Okay? Now, if all you did was add the numbers together, and you came up with this, no go. Okay? This is the exact answer. The fraction. This is a rounded answer. Okay? Either way is acceptable. Cool. Moving on. Now, I'm not going to go where this comes from, but this is a formula you need to memorize. Another one. The sum of a certain number of terms of a geometric sequence is equal to the first term, A, times 1 minus R, and R is the common ratio of terms, to the power of n, where n is the number of terms, over 1 minus the ratio. Now, notice that I put this in parentheses. The parentheses are going to guarantee that if R is a negative number or a fraction, that you'll get this right if you type it into a calculator. If you don't put the R around if you don't put the parentheses around the R and it's a fraction or it's negative, you're likely to get it wrong. In fact, if it's you're likely to get it wrong. So remember the parentheses. If you do that, you can type it in just like it looks. Let me show you. The sum of the first n terms of this sequence. Well, the sum of this is equal to the sum of the first n terms. Wow. Well, is going to be equal to, let's think about this, the first term. Well, what's the first term? Well, the first term is 1/2 to the power of 1. Well, that's just 1/2. So 1/2 times 1 minus the ratio. Well, the ratio is the 1/2. It's easy to see the ratio because it's always the base of an exponential to the power of n. Okay. All over 1 minus 1/2. Let's see if I can put this together a little bit. If I multiply 1 minus 1/2 on the bottom is 1/2, and this is 1 minus 1/2 to the power of n. I can't simplify that. But if I go 1 times the top, I just get 1 minus 1/2 to the power of n over 2 times 1/2. Well, that's just 1. So I end up with 1 minus 1/2 to the power of n. And that's as far as I can get. But what I've just found is a formula that I could find the sum of any n terms. I just have to put in n on that, of that particular sequence. Cool. Now, I'm not usually going to do this because usually I'm just finding this for one time, and I don't care about finding a generic formula. So let's look at this. Find the sum of the first 6 terms. And I know you can go 27, 9, 3, 1, 1/3, 1/9, 1/27, and add those all together. However, you will not get credit. You need to get used to using the formulas. Okay? So let's look at this. Sum of the first 6 terms. Is it geometric? 27 divided by 3 is 9. Divided by 3 is 3. Yeah. My ratio is 9 over 27, which is 1/3, because it's dividing by 3, which is the same as multiplying by 1/3 every single time. Okay, so the sum of 6 terms is going to be the first term, which I know is 27, all times 1 minus 1/3, put that in parentheses, to the power of 6, all over 1 minus 1/3. I'm going to type that in my calculator. 27 times, parentheses, big fraction, 1 minus, in parentheses, 1/3, to the power of 6, all over 1 minus 1/3. And I get 364/9. And I know that if I change that to a decimal, it's going to be a repeating thing. So I'm just going to leave it like that. Find the sum of the first 10 terms of this. 3, 6, 12, 3 times 2, right? 6 divided by 3 is 2. So my ratio is 2. And this is a geometric sequence. So the sum of the first 10 terms is equal to the first term, which is 3, times 1 minus the ratio, which is a 2, to the power of 10, all over 1 minus 2. Now, if this one you leave off the parentheses in there, you'll be okay, but I'm wanting to make it a habit, so I'm going to write them in there. 3 times big fraction, 3, parentheses, big fraction, 1 minus, parentheses, 2, close parentheses, to the power of 10, all over 1 minus 2. Okay. And that gives me 3,069. So again, I'm just typing exactly what I see into my calculator. That's all I'm doing. Okay? And as long as I make sure that I write what I'm typing down, see? There we go. I can use that. So let's look at something else. Whoa, this is summation notation. Cool, huh? I like this. First, recognize, look at this. See the base with the exponent? This is geometric. That's your first hint on this, is you should be able to look at a summation and decide, is it arithmetic, is it geometric, or is it neither? If it's neither, the best you can do is put in all your numbers and then just go plus, 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 and add all the things you get. But this is geometric, so which means I can use a formula. The formula says of the first 6 terms, because there's how many terms. I'm adding the first term to the 6th term. Is the first term. Now, there's 2 ways to get the first term. if I want the first term, I can always put in a 1 into that formula. Negative 1 minus 1 is 0. Negative 1 to negative 1/2 to the power of 0 is 1. 12 times 1 is 12. And so I go, oh, the first term is 12. Or I can look and say, hey, this looks like a times r to the n minus 1. So the first term, just from matching it up with the equation, is 12. So 12 times 1 minus the ratio, which is negative 1/2. And I could find the ratio by finding the first term and the second term. And the second term is going to be 12 times negative 1/2 to the power of 2 minus 1, which will be negative 6. And I could take, hey, negative 6 over 12. That gives me negative 1/2. So I could find the second term and the first term and divide them and get the ratio. Or I can look at the formula right there and notice, hey, that's the first term. That's the ratio. 1 minus 1/2 to the power of 6 all over 1 minus a negative 1/2. Cool. And I'm actually going to type that in exactly like I wrote it there. Okay? 1 minus a negative 1/2. And I've already had this formula typed in for the last problem. So I'm just changing that ratio to negative 1/2. See? Check it out. Cool. Equals 1,023 5/12. Okay? 1,023 512ths. This does give me a decimal, 1.998400468. I don't want to write it down. I'm just going to leave it. Okay, cool. Now, geometric series. If the ratio is small, think about a sequence where it's getting smaller all the time, like 1, 1/2, 1/4, 1/8, 1/16. Those numbers are getting smaller every single step of the way. Well, eventually they're going to get so small that they are indistinguishable from 0. That's what we say is a sequence that converges. It's converging down to a lowest value, which is essentially 0. That happens if the absolute value of your ratio is less than 1. So it's getting smaller every time. If the sequence is getting smaller, it's going to converge. If the sequence is getting bigger, it diverges. Any convergent sequence, I can find the infinite sum. I can add up all the terms forevermore, infinitely. Cool. Okay? And that sequence is, the sum is equal to this. The sum of an infinite sequence is equal to the first term all over 1 minus the ratio. This is another one to memorize. You know it. Need to know it. Okay? Now, let's try it. Determine whether it's going to converge or diverge. Converges, find its sum. Does this converge? Well, 2 4/3, 8/9. Yeah, these fractions are getting smaller. So it's going to converge. Well, if it converges, then I can do the infinite sum is equal to the first term over 1 minus the ratio. Well, the first term is 2, but the ratio I don't know, and I don't see it easily. But if I take the second term and I divide it by the first term, 4/3 divided by 2, that gives me, 2/3. There's my ratio, 2 divided by 2/3, and I know 2 divided by 2/3 is 6. So all of these numbers infinitely are going to add up to 6. Cool. Determine whether this series is going to converge or diverge. Well, I know it's going to converge because first, I recognize this is geometric because it has that exponential with the power on it. And I know that that's the ratio. And 1/3 is less than 1. So this is going to converge. Well, to converge, to find the sum, I need the first term. Well, the first term is 8, and I know that because this is in that form. First term times the ratio to the n minus 1. First term is 8, all over 1 minus the ratio of 1/3. So 1 minus 1/3 is 2/3. 2/3. And 8 divided by 2/3 is 12. So these will all add up to 12. This is pretty slick. I love these things. Infinite sums are nice because the formula is nice and it's easier. Let's look at something else. Is this going to converge or diverge? 4, negative 8/3, 16/9, 32. Well, 4, big number. 32/7, that's just a little bit bigger than 1. So this is getting smaller. So this is going to converge. Okay? The ratio, I don't know what the ratio is. -8/3, all divided by 1. No, dummy. The ratio, -8/3 divided by 4. Sorry. Well, -8/3 divided by 4. Isn't that -2/3, I think? -8/3 divided by 4 gives me, yeah, -2/3. There's my ratio. Okay, so the sum of the infinite terms is going to be the first term, which is 4, all over 1 minus the ratio, which is -2/3. Well, if I type that in, I'm typing it in exactly like it looks. 4 over 1 minus the -2/3. Oops. 2/3. 1 minus a negative. See? Oh, there it is. Okay. Typed in just like it looks. Equals 12/5. And you're like, wait a second. 12/5. That's like 2.4. How? What? 4? And it starts out with 4 and then it adds up to 2.4. Well, yeah, but you see, it's subtracting. Starts with a number, subtracts with a number that's smaller than that. Adds a number, subtracts a number smaller. So the net result is going to be positive, right? Yeah. Net result's going to be positive, but it's going to be smaller than what you started with. Cool. So look at this. A statistician knows that a town population, oh, this is a story problem. You're probably, yeah, duh, you started reading it. Sorry. Long day already. A statistician knows that a town population of 3,500 people has a growth rate of 6%. That means it's going to go up 6% every year. What should she predict the population be in 20 years? Well, this is geometric, or I can treat it like geometric, because if I start with 3,500, there's my starting point. And then the rate of growth every year is it adds 6%. Well, 6% is 0.06. But see, if I multiply this by 0.06, that number goes down. So to make it grow by that much, I need to multiply by 1.06. 100% and 6 more? Yeah. I can go that the 20th year, hey, that's just going to be the first year, that's 3,500 times the times that growth rate of 1.06 to the power of 20 minus 1. This is the very first formula we looked at. So if I type that number in there, 3,500 times 1.06 to the power of 20 minus 1, which is 19, and I get 10,589.598. Well, if she predicted that population, she's predicting there's a half a dude walking around. No, this is 10,590. Okay? Or I'd take 8,589 because you could argue, well, 20 years, it's not quite going to be 90. So you could go down, but it's got to be rounded to the nearest it's got to be rounded to a whole number. Excuse me. So it's talking about a population. Moving on. Let's take a look at this. Wow. A lot of stuff. Suppose that the motion of an object through a certain medium is such that it travels 90% as far each second as it did in the preceding second. If it moves 50 feet in the first second, wow. This is like those cop shows or CSI shows where they shoot a bullet into the gel and it slows down and eventually it stops. And you can say, oh, because it went this far, we know that they shot from this far away. Yeah. Or, yeah, that's exactly what this is like. Okay, cool. So, in the 15th second, let me think. If it moves 50 feet the first second. So I'm thinking the first second, it moves 50 feet. The second, it's going to move 90% of that. Well, 90% of 50, that's just times 0.9, right? Yeah, because that's 90%. 90% of 50 is 45. 45 times 0.9 is 40.5, and so forth. Okay. So how much is it going to travel in the 15th second? Well, that just wants to know what's the 15th term. Well, the 15th term is going to be the first term, which is 50, times the ratio, which is 0.90, times, or to the power of n minus 1, which is 15 minus 1. I'm looking at this. This sequence is getting smaller every time, so it's converging, right? Yeah. Okay. So eventually it's going to get to the point where this thing stops, right? The bullet's going to go where the movement is so small that I can't distinguish it between not moving, but it's stopped. Cool. Okay. What is this? 50. My chair is squeaking. I need to fix that. 0.9 to the power of 15 minus 1, that's 14. I get 11.438. And since this is in feet, this is going to be feet. How far did it travel during the first 15 seconds? So this is just the 15th second, it went 11 feet. But during the first 15 seconds, that thing, bang, the thing's going, and then 15 seconds, how far does it go? The difference between A and B is this is asking for the sum of the first 15 seconds. Well, that's a different formula. And this is, so sum of the first 15 seconds, that's the first term, which is 50, times 1 minus the ratio, which is 0.90. Or no. No. I'm right. 0.9. Sorry, I'm just second guessing myself. Oh, I gotta go. Wait. Sorry. Oh, sorry. 1 minus. Sorry, I need to select the right thing. 1 minus 0.9 to the power of 15 all over 1 minus 0.9. I'm just using the summation formula. So we used this formula, a sub n equals e sub 1 times r to the power of n minus 1. Use this formula, s sub n equals a sub 1 times 1 minus r to the power of n all over 1 minus r. And I'll bet we're going to use this formula eventually, s sub infinity equals the first term over 1 minus the ratio. So if I enter this in my calculator, 50 times big fraction 1 minus in my parentheses 0.9 to the power of 15 all over 1 minus 0.9. There I get 397.054, and this is going to be feet. Now, how far will it travel in the nth second? The nth second? The infinitieth second? Well, if it's getting smaller every time, that means in the infinitieth second, it's going to travel effectively 0 feet. Right? Yeah. Because if I put nth nth second. This is different. Sorry. That's in the infinite nth second. The nth second, how far does it travel in the nth second? Well, that's a sub n equals a sub 1, or yeah, and I already know this formula. A sub 1, which is 50 times 0.9 to the power of n minus 1. Nth second. That's nth second. I was thinking the infinitieth second. Maybe that's what I'm asking myself. In the last second, it's not going to travel because it's going there. Okay, so here, let's think about this. How many seconds will pass before the object travels less than 15 feet? Well, if this is the distance that it travels in the nth second, I want to know when 50 times 0.9 to the power of n minus 1 is less than 15. Huh. That's curious. If I solve that, I'm going to divide by 50. And I get 0.9 to the n minus 1 is less than 15 over 50. 15 divided by 50 gives me 0.3. Okay. How do I do this? Oh, you know what? I could set, this could be rewritten as a logarithm. I could go the log base 0.9. See, I said log base 0.9 and I did something different. I could rewrite this and I could go, this is an exponential. Actually, you know what? Nope, sorry. I'm going to back off. Log base 0.9 of 0.3 is equal to n minus 1, right? And then I add 1 on each side. I did just change it to an equation so it's easier for me to think about. Log base 0.9 of 0.3 plus 1 equals n. That's going to be the number of seconds that that it will travel exactly 15 feet. So if I type that in my calculator, and yeah, I can do that log base 0.9. So I'm going to do that. If you couldn't, you'd just do the change of base formula. Oops. Plus 1. And I get 12.42. N equals 12.42, which tells me that n is greater than 12.42. And now, since I'm thinking of this as a sequence, I can't have a decimal second. So at 12 seconds, it's still traveling more than 15 feet. So n has to be greater than or equal to 13 before it's going to travel less than 15 feet. Cool, that's an interesting question. How far will it travel before coming to rest? That means it stops. Well, it's going to stop at the infinite sum. Whoa. How many seconds will it travel? Or how far will it travel before coming to rest? So when it stops, that's when it goes infinitely long. So really, this is asking for the sum of all the infinite terms. And the sum of the infinite terms is just the first term, which is 50 over 1 minus the ratio, which is the 0.9. Well, 1 minus 0.9 is 0.1, and 50 divided by 0.1 in my calculator is 500. So going through whatever this medium is, this thing will travel 500 feet before it stops. So a geometric sequence, this is a great example of a contextual problem. As something's traveling in friction against something is acting on it, it's going to slow down proportionally every single second. And if I let this sequence go, I find the proportion, I let the infinite sum go, that will give me the distance it's going till it stops. Cool little problem. I like this. Check this out. Assume this is geometric. I'm not going to assume it's geometric. That's stupid. We all know what assume means. 5/3, 10/9. Well, if it's geometric, then I can take this 10/9 divided by 5/3, and that will give me its ratio. So I just take the second term divided by the first term. 10/9 divided by 5/3 gives me 2/3. Okay, so that's my ratio. The ratio is 2/3 if it's geometric. Well, 10/9 times 2/3. 10 times 2 is 20. 9 times 3 is 27. Okay, 20 times 2 is 3 times 3 is 9 times 3, 5, 10, 20. Shouldn't this be 40? I think I found a typo in this example. Because if I'm multiplying this by 2/3, the top should multiply by 2, right? 5, 10, 20, 40. 3 times 3 is 9, times 3 is 27. So this should be a 40. Assume that it's geometric. Well, I'm just going to go 40 times 2, 80 times 2, so 160, 320, 640, 1280, 2560, 5120. Yeah, it's the 40 was wrong. So I'm glad that I looked at that, because the way it's written, it's not geometric, because this is times 2/3, that times 2/3, that's not times 2/3. So we're going to fix the problem. There it is. Find the sum of that. Okay. Using appropriate formulas. Yikes. Well, I know the sum is equal to the first term. Well, that's 5/3 times 1 minus the ratio. When we just found that, it's 2/3. 1 minus 2/3 here. But here I need n. I need the number of terms. Here's how I would do this. There's complicated ways to find what term that is. Let me show you the complicated way, then let me show you what I would really do. The complicated way would say, this 5,120 over this 177,147, that's equal to so this is the nth term, right? The first term times the ratio to the power of n minus 1. I need to solve that, so I'm going to divide by 5/3. And that gives me 5120 all over 177,147. And I'm going to divide this by 5/3. That gives me 1,024 over, see, if you already don't like it, I agree with you, 59,049. And that equals 2/3 to the power of n minus 1. Okay. And now I'm looking at that and saying, that's an exponential problem. I'm going to take a log. The log, base 2/3, yuck, of 1,024 over 59049 equals n minus 1. And then if I evaluate this, if I take the log base 2/3 of this 1,024 all over 59049, I type that in my calculator, check what I get. Ha! 10. 10 equals n minus 1, and then I add 1 to each side. I get n equals 11. Beautiful. Yuck. I hate it. I don't like that. Here's what I would do. I would go like this. Look at the top. 5 times 2. I know the top's multiplying by 2 because it's 2/3, right? 5 times 2 is 10. Times 2. Check this out. 10 times 2 is 20. There's the third term, fourth term, fifth term, sixth term, seventh term, eighth term, ninth term, 10th term, 11th term, 5120. I just count it until I hit it, and I say, oh, I hit my calculator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's the 11th term. Beautiful. That's okay. I don't have to use the formula to find the sum, to find the number of terms. I just need to use a formula to find the sum. That's how I would find the term. With geometric formulas, you're going to have to use a logarithm to find that n if you're going to solve it that way. They generally tend to be pretty quick. Just multiply times, count how many times you did it. Okay, just be careful. Now, if I type that in my calculator, just like it looks, 5/3 times big fraction, 1 minus, in the parentheses, 2/3 to the power of 11 all over 1 minus 2/3. I'm going to get, this won't do a nice fraction for me, but it does give me 4.942149. There it is. Whew. Yuck. I don't like this problem at all, but this is as complicated as it gets. Guys, that's it. I'll see you next time. Bye-bye.